In this video, we're going to look at 10.6, finding segment lengths in circles. So please notice that it says segment lengths in circles, and we're only going to be talking about segments, no longer angles in this lesson. So the first thing we need to do is look at some definitions. So the first one is segments of a chord. So what exactly is segments of a chord? The definition is when two chords intersect in the interior of a circle. So I'm going to draw a chord here, and I'm going to draw a chord here. It can be anywhere in the circle. It states each chord is divided up into segments. So if you'll notice here, here's piece 1, here's piece 2, here's piece 3, here's piece 4. So if chords intersect, you're going to have different segments. Now, there is something called the secant segment, okay? In the secant segment, I need you to notice here that it's the whole piece. So that's a secant segment. It's a secant going through a circle, and it is a segment that contains the chord. Here is the chord, and it has exactly one outside. So you have an external segment and the chord. So this is a part, this external secant or segment, and the chord is a part, but the secant segment is a whole. Now you can also see here the external segment is going to always be outside, but it's a part. Now the tangent segment here is in blue. Notice it's outside and there's just one piece. So we're going to talk about that in just a second. Now, moving on, all of these definitions lead to three very important theorems for segment lengths in circles. So the first theorem we're going to look at is theorem 10.14, segments of a chord theorem. It says if two chords intersect in the interior of the circle, in our picture they are intersecting at E, then the product, that's multiply, of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Now, this is what this means. This means that segment EA multiplied by segment EB equals EC times ED. So EA times EB equals EC times ED. Now, this is the way I remember this. It is part times part of the first segment equal to part times part of the second one. Now, you can remember these a little bit better if you know why this is happening. What makes this happen? Well, we've actually already studied this year. Here is the proof of theorem 10.14. So, same picture that I have here. Here is what we're trying to prove. That's what we have up there. And we can do this in 6 steps. So the first thing we need is two intersecting chords in the same circle. That was given. The second step tells us to draw AC and draw BD. And we can do that because that's just definition of a line or a definition of a line segment. Now the next part is interesting. It says angle A is congruent to angle D. Now why is that? Well, they intercept the same arc. Same thing, so I'm going to mark those. And the same thing with angle B and angle C, they intercept this arc. Now we learned that in a previous lesson, that is theorem 10.8. That's when two inscribed angles intercept the same arc, then the angles are congruent. So now look what we have. We have this top triangle and this bottom triangle. We now know the triangles are similar because of angle-angle similarity. Well, if the triangles are similar, we have proportional parts. Now, in this little statement here, it says EA, and remember we have triangles on the top and the bottom. We have EA, which is the small part of the first triangle, is proportionate to ED, the small part of the bottom triangle, just like the long part is proportional to EB. So it's just two triangles that are similar. So now, when I do this to solve the problem, I get EA times EB equals this side here, EC times ED, and we simply know that as the cross multiply property. So the most important thing right here is knowing what to do when we get numbers. So if it's inside the circle, you're going to go part times part equals part times part and keep those parts on the same chord. Now let's look at segments of a secant theorem. Notice now the secants have outside parts, and you can see that here in red. And it states if two secant segments share the same endpoint outside the circle, this is E, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the same thing. Now, this is what this is saying. This one is saying EA times EB equals EC times ED. Now, EA is the outside external segment. EB is the whole thing. That is equal to outside segment to ED, the whole thing. So this is the way I remember this one. This is part times whole equals part times whole. Now again, you will remember these more if you really understand why this is happening. Now all of these have this in common. It's just about similar triangles. So here is the proof of 1015. Same picture, same theorem. Given EB and ED are secant segments. Step 2, draw AD. Now notice that's a triangle. And BC, that's another triangle. Now, why is B and D congruent in step 3? Well, they are intersecting the same arc of AC. So it's still 10.8. But that only gives us one angle. So in step 4, you'll notice we have angle E is congruent to angle E. Well, we know that because it's the same angle. It's the same angle in the top and bottom triangles. Well, now we have triangles congruent again. Triangles BCE, which is that top triangle, is congruent to DAE, which is the bottom triangle, and we know that because of angle-angle similarity. Now again, if the triangles are proportional or similar, then the parts are proportional. Sorry about that. So we have this small part is proportional to this small part, and ED is proportionate to EB. Okay, then we cross multiply again. We cross multiply there, and that's why this is happening. So it's just the cross multiply property again. Now I need you to kind of stop for a second and notice how this one came outside. So these segments came outside, so we had to go to the whole pieces. On the previous one they were inside, so it was part times part. Now we have one more to look at, and this is when you have a secant and a tangent. So here is the secant, and the blue one is the tangent. So the theorem reads, if a secant segment and a tangent segment share an endpoint outside the circle, in this situation it is E, then the product of the lengths of the secant segment and its external segment equals the square of the tangent segment. Now this is what this is saying. EA is the tangent segment. The square of that is equal to EC times ED. Now, if you will notice, EA squared is just EA times EA. So this is the part and the whole. It's the same thing, where EC is the part and this is the whole. Okay, so this is a longer proof, but it follows just like the other proofs. Okay, so now looking at this proof, number 1, a secant and tangent segment share a common endpoint on the outside of the circle. That's going to be E again, and that is given. And it says draw AC. Now I want you to notice here that I'm drawing that small triangle on the left. And then it tells me to draw AD. Now, that just created this triangle here, but I need you to kind of focus on the bigger triangle. So this triangle here, the bigger one's what I need for you to focus on. So I'm going to color this triangle in over here so you can kind of see that that's the small triangle, and then we have the bigger triangle. Now, step 3, here is step 3. It says the measure of ADC, which is right here, is 1/2 of AC. Well, we know that to be true because that is an inscribed angle theorem. It's 1/2 of that. Now, if I go to step 4 here is step 4. It says CAE, which is up here, kind of where I've got this colored, so I'll kind of color it in a little bit better. That angle is also 1/2 of the measure of AC. And it's kind of acting like the inscribed angle theorem, but we had a name for it. It was 1011. It's a tangent and a chord. It's still 1/2 of the intercepted arc. Now, if you'll notice here and here, that's the same thing. So in step 5, we can say those angles are now congruent, okay? Because we just substitute. So now, if those are now congruent, you can clearly see that they are, then we can move to angle E. So step 6, I have angle E is congruent because of the reflexive property. Now, you've got to kind of stop and think, what is it congruent in? Well, angle E is in this small triangle that I have colored completely in, and angle E is in the big triangle, EAD. So now that small triangle that I have colored in is congruent to DEA, the big triangle, by angle-angle similarity. So now, since those triangles are similar, I've got some proportional pieces. EA, okay, is proportionate to EC, okay, just like ED, see the big piece there, is proportionate to EA again, okay? So here, you kind of follow along, and then we're just going to cross multiply again, and we have that property, okay? So now, what we're going to do is kind of just quickly go through some problems of just these in action. Now, I need you to notice 1, 2, 3, I have an example of each theorem. So, for number 1, it says find ML and JK using theorem 10.14. Now remember, it is part times part equals part times part. So, I am going to say x plus 3 times x plus 1. So that was this chord, just like that part times that part. Now the reason why I made you review Algebra 1 yesterday is for these problems. We have a quadratic that's going to appear. So we have x squared, we have 1x, we have plus 3x, we have plus 3 equals x squared plus 5x. Now, lucky for us, when we go to get this x squared together over here, those cancel out. So now I have 4x plus 3 equals 5x. Subtract the 4x over, and I get 3 equals x. Now, the problem tells me to find ML. So ML is this whole piece right here. So here is ML. So this is 3 plus 3, which is 6. And this is 3 plus 1, which is 4. So ML is 10. JK, on the other hand, JK is the whole piece on this other one. So that's going to make that 8. That's going to make that 3. So JK is going to be 11. So part times part equals part times part. Now, for question number 2, it's theorem 10.15. This is going to be part times whole, part times whole. So 6 times 10, because I have to add those two up, equals part times whole. The only way I can add x and 5 together is just to say x plus 5 or 5 plus x. So this is 60 equals 5x plus 25. Subtract 25 from the other side, and we're going to get 35 equals 5x. Divide by 5. 7 equals x. Now, that's all we had to do for that one. Now, for number 3, this is going to do 10/16. We have a tangent and a segment. And remember, this one could still be part times whole. So 14 times 14, that's 14 squared, equals x times x plus 12. Now, 14 squared is 196, and that is going to equal x squared plus 12x. We're going to have to take the 196 over, so we're going to make that a negative 196. And the next step I'm going to do is I'm going to see if this will factor. So I reviewed that with you yesterday, and if we do b squared minus 4ac, we are going to get 928. But 928 is not a perfect square. Therefore, this will not factor. Therefore, I'm going to do the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac, which we just figured that out to be 928, divided by 2 times a. Now, this, of course, would have to be put into the calculator. And lucky for us, x is our s, so when we calculate that on the calculator, we're going to get 2 answers. We're going to throw one away, but the answer that should come out is 9.32. Since our s is x, this is going to be 9.23. So it's very important that you know your Algebra 1 skills here, and with your Algebra 1 skills, you're going to be able to breeze through the quadratic part.